Okay, this little video is more practice on section 2. You know the general idea, the intuitive idea. The function values can be made arbitrarily close to L by picking x sufficiently close to A. The closer x gets to A, the closer f of x gets to L. Okay, so you have that idea. Now, I'm going to go into the precise definition. I'm going to assume that you've already watched the other video. So this is just a quick video getting you ready for the quiz, okay? Before we talk about that, though, you have to make sure you have a good handle on absolute value inequalities. If you have an absolute value of something less than a number, what's inside the absolute values would be between negative delta and positive delta. Delta is just a positive number. I'm sorry, it looks a lot like an 8, but it's not. It's just some positive constant, okay? So the way you solve it is you would add a to both sides, and if you want to solve this for x, it says x is between a minus delta and a plus delta. So think of it as x is somewhere in here, somewhere between, in this interval between a minus delta and a plus delta. And we're also going to need this one here. Look, if you have the absolute value of f of x minus L is less than some positive number epsilon, that means what's inside the absolute values is between negative epsilon and positive epsilon. You add L to all three sides. So f of x, if you want to solve this for f of x is somewhere in this interval between L minus epsilon and L plus epsilon. You need to know that first. Okay, so what the absolute value inequality is just a shortcut way to write a double inequality. Okay, that's all. So here's the precise definition. It says, let f be a function defined on some open interval that contains a number a. When it says that, it means it has to be defined on both sides of a, except possibly at a itself. In other words, you could have a hole. In fact, this picture I just drew here has a hole at x equal a. You see that? The function does not have to be defined at that value for the limit to exist, and we've seen that in section 2.2 and 2.3 already. The limit exists. The limit is x goes to a of f of x equals L exists if for any epsilon greater than 0. In other words, that's this. Think of this as an error bound along the y-axis. This is the distance that f of x is from L. No matter how small you make that, in other words, no matter how small epsilon is, you can always make the function values in that band by finding a corresponding interval. This interval is going to have radius delta, like we were talking about earlier, so that if x minus a absolute value is less than delta, that just means that x is in this interval, right between here and here, then f of x absolute value minus L is less than epsilon. That means f of x is in this interval here. Now you may wonder, what's this right here? This 0 is less than the absolute value of x minus a. That just means we don't care what happens when x equals a. In other words, you could have a hole. That's what this says. It doesn't matter what happens when x equals a. Because if x equals a, this equals 0, right? So as long as it's greater than 0 means x is not equal to a. So that's why they put that there. So that's the definition. Now, in these homework problems, you are going to be given an epsilon, in other words, the error bound on the y-axis around L, and you have to find the corresponding delta interval around A. And the way we're going to do it is we're going to find these two x values, the x values where the graph crosses the error bound around L, and we're going to find x1 and we're going to find x2, and then we're going to find the distances they are from A, and whichever distance is the smaller distance, that's what we're going to call delta. If you use the bigger one, then on one side they would be outside the interval, and some of the f of x's wouldn't be in the band, so always use the smaller radius around A. So that's the idea. Let's look at an example. Find delta so that if absolute value x minus 3 is less than delta, then absolute value x plus 1 minus 2 is less than epsilon. Okay, so first you have to figure out what's going on here. This is your f of x, so f of x is equal to square root of x plus 1. This is your L, so the limit's 2. This is your epsilon, so the radius of that interval is 0.1, and you have to find this delta interval around 3. So the picture looks kind of like this. This is your function. Now, by the way, what is this saying? It's saying the limit as x goes to 3 of the function equals the limit. Is that even true? Yeah, it is true, isn't it? So this is all this is saying. Okay, so going back to the problem. So they're giving you since epsilon's 0.1, and this is your limit 2, L plus epsilon is 2.1, L minus epsilon is 1.9. And you need to find these two x values, x1 and x2, that are around 3. And the way you do it is you notice that x1, f of x1 here has to equal 1.9 because it lies on the graph and it lies on the error bound, right? The lower limit of the error bound. So you would solve that equation, f of x1 equals 1.9, square both sides and subtract 1, so x1 is 2.61. This x2 value, f of x2 has to be 2.1, so that says that f of x2 equals 2.1. You square both sides and subtract 1, you get this. Now, the answer is whichever distance is small. You take 3 minus x1, and you get 0.39. Here you take x2 minus 3, and you get 0.41. We're going to use the smaller one, so that's why we picked 0.39. Okay, so I'm going to have you try one now. Try this one. Hit the pause button. Find delta so that if absolute value x minus 3 is less than delta, then f of x, which is x minus 1 cubed minus 8, is less than 0.05. Round your answer to thousands. We'll go over this in just a minute. Okay, so first of all, it's important that you understand what's f of x. F of x is this. This is L, and this is A, and this is epsilon. So this is just saying the limit as x goes to 3 of f of x equals 8. And it does, right? It does. That's nice. So the graph looks like this. It's x cubed minus x minus 1 cubed. It looks kind of like this. And so you're given epsilon, so this would be 8.05, 7.95. x1, when you plug it into the function, it has to be 7.95. And if you solve that for x1, you get x1 is about 2.99582. And then if you plug x2 into the function, it has to be 8.05. And then you could take the cube root, add 1, and you get x2 is about this. But remember, you have to take this distance from 3. So 3 minus x1, 3 minus this is about this. And then you would take x2 minus 3, and you get this. You want to round it to hundredths. Which is the smaller one? Well, technically, let's see. Technically, this is the smaller one. But rounded to hundredths, rounded to thousands, they're both 0.004. All right, there you go. All right, that's pretty much it. Let me say one last thing here. There's 2 more limits, definitions. My feeling is if you understand the first one, then the others are kind of similar. What does it mean to say the limit as x goes to a of f of x equals infinity? The function has to blow up, right? Both sides have to get close to infinity. So the question is, how high does it have to go? If the graph is getting close to infinity, how high does it have to go? And the answer is, for every m, in other words, m is some big positive number, you can actually find an interval around a. That's your delta interval around a, right? That's what this says. X is between a minus delta and a plus delta. The function values, all the function values of these x values in this interval is higher than m. That's what it means to say the limit as x goes to a equals infinity. And you might think the higher m, the smaller delta, right? The higher that you insist the function to be, the closer you have to be to a. And this, similarly, it's true with going to negative infinity. I'm not going to talk about this. You can just read this for yourself. You go ahead and hit the pause button. But let's do one last example here. So find delta so that if absolute value x minus 3 is less than delta, that means x is between 3 minus delta and 3 plus delta, then the function value is above 1,000. So your function is 5 over x minus 3 squared, and the m value is 1,000. So how do you find your delta? That's all you really need to do. Similarly, we're going to find these two x1 and x2 values. Notice that f of x1 has to equal 1,000. So when you solve this for x1, multiply by x1 minus 3 squared and divide by 1,000. And then I took the square root. Now when you take the square root, look, notice you get 2 answers. You get plus or minus the square root of 200, which is plus or minus this. So I've actually found both of them at the same time. If you notice, x2 is going to be 3 plus this number, and x1 is going to be 3 minus this number. So I actually found both of them at the same time. But the thing is, if you think about it, isn't delta this, right? It's a symmetric number around 3, so your delta is just 1 over 10 squared root 2. Rounded to thousands, it's 0.071. All righty, that's it. Good luck. Talk to you later. Bye.